Welcome back to the series of lectures on high performance scientific computing. In today's class, we will be looking at the most important bits about how to decide what parts of the program to parallelize. And for that, we need to compile and profile the sequential code. We will then look at the explanation of multi-core programming, and then we will also see how to compile and profile multi-core code. Through this process, we will see how the iterative process of improving your codes happens. So, the first thing we will look at compiling sequential code for using the NVIDIA suite of compilers. Similar process exists for the GCC suite and other compilers as well. So, if you look at the NVIDIA's HPC compilers, which were formerly known as the PGI compilers, they all have NVIDIA related new names, but the old names which are related to PGI will also work. For example, to compile the code using C, we will use the NVC compiler, which was formerly known as PGCC. Similarly, NVC++ will be used to compile C++ code. This used to be known as PGC++. We have NV Fortran, which used to be PG Fortran, PGF90, PGF95 or PGF77. This is used to compile Fortran code. And the -fast flag instructs the compiler to optimize the code to the best of its abilities. So, this is an example of how you would use the compiler. So, you would either say PGCC -fast and then the source code, in this case it is main.c, or you would, if it's a C++ code, it would be main.cpp, or for Fortran, main.f90. There are a few other information bits that you can get from this compiler using what is called as the minfo flag. The minfo flag will instruct the compiler to print feedback about the compiled code. Now, let us see what kind of information we can get back from the compiler. If you say minfo is equal to accel, which will give us information about which parts of the code were accelerated using OpenACC. For example, you have been learning about how to use OpenACC directives. So, if your code has OpenACC, then the flag -minfo equal to accel will give us information which parts of the code are accelerated. minfo equals to OPT or optimization will give you information about all the code optimizations that were done. Remember, there is a whole bunch of code optimization which the compiler can do once it reads through the code and parses it. minfo equal to all will give all code feedback, whether it is positive or it is negative. So, for example, you could use flags like -fast, which starts optimizing the code, and you can give -minfo equal to all, and it will give you all the information about the code where the optimizations have been done and whether they positively or adversely affect your code. Let's take a little deeper look into this NVIDIA Nsight family of tools, because this is very useful to us in helping profiling the code, and which then helps us further to optimize our program. Remember, our old friend Amdahl's law depends highly on tools like this to figure out which parts of the code can be parallelized, which parts of the code require more efficiency, and so on and so forth. So, this is typically the workflow for this Nsight product family. So, you have these Nsight systems which give you comprehensive workload level performance, and then you can look at it towards two sets. One is the compute side, where you can get detailed kernel performance from CUDA. You can then look at how CUDA kernels are working, you can analyze the system, and then sort of re-optimize the code. The other way is to go towards graphics to see, optimize and debug graphic workloads, which we are not really concerned with as much in the scientific computing business. So, our work will be typically in the compute side. So, now let us look at how this tool looks. This is a screenshot of how the output from the tool actually looks. Now, this bit of slide looks extremely complicated. Let us decipher this a little bit to begin with. The few things that first you will notice is what is called as thread/core migration. Remember, we are running these systems on multiple cores. There are multiple threads also running. So when the OS is sort of scheduling these threads on different cores, they come in and out of the processor. This bit of graphical information which is being pointed out tells you how this thread/core migration is taking place, where which thread is going, on which core it is getting executed, whether it's being swapped back out for some other execution, and all such sundry information. Now, for the code to run efficiently, you need to have the minimum amount of such migrations, and you have to mitigate this. Here on the left side panel, you will get more information about the processes and the threads that are actually running on the system. You will also figure out what the thread state is, as in whether the thread is actually executing, whether it is waiting, whether it is blocked. So you can get a lot of information about the thread on how its performance is. Ideally, they should all be in a state where the thread is not waiting to get executed, but that's rarely the case because you have multiple threads and you probably have fewer resources for these threads to work. The thread could be waiting for many resources, including compute resources, and also waiting for data from the memory. Here on the left side, you get both the CUDA and the OpenGL API traces. What do we mean by that? So remember, we are doing CUDA calls. Even if you are using OpenACC, underneath the code is now converted into graphic calls. So you're now looking at the traces over there. If you used special libraries, like for example, you used cuBLAS, which is a linear algebra library which is specifically tuned to get executed on NVIDIA CUDA devices, or the deep neural network library CUDNN. So this looks at the library call traces. So you also look at how the kernel and memory transfer activities are taking place, because that is another important time consuming process where you're transferring data back and forth and you're transferring the kernel information back and forth. Finally, if there are multiple GPUs, right at the bottom you will get to see what is really happening on each of those GPUs. Remember that each system can have multiple devices connected to them, and you could have multiple GPUs. Each of those GPUs could be similar or dissimilar, and they'll have different loads running on them. Let's begin with the idea of profiling the sequential code. So let's say we want to develop your code using OpenACC. What is typically the OpenACC development cycle? First, you need to analyze your code to determine most likely the places where parallelization or optimization is needed. Then you parallelize your code by starting with the most time-consuming parts of the code. You check for the correctness of your code. Remember that reproducibility is one of the most important things. It doesn't matter whether you're running the code on CPU, whether you're running the code on GPU using NVIDIA CUDA, or if you're running it using directive-based programming like OpenACC, whether you're parallelizing the code using OpenMP on shared memory systems, or you're using MPI on distributed memory systems. Your code should always give the same answer. That is about checking for correctness, because it has got no point if it gives you different answers in different paradigms. We then analyze it again. Finally, we optimize your code, then improve it. We look at the speed up data, we calculate what is the performance gain that we are getting from parallelization, and then we go back to analyzing the code. And we do this process iteratively over many loops to get the maximum possible efficiency out of parallelization for the code, and we stop once we start getting reasonable performance improvements. So now let's look a little bit deeper in what we do in analyzing codes. So for that, you have to first profile the sequential code. For that, you need to run your code. So typically you would run your code by first compiling it and then executing it in a terminal window like this. And then you will figure out how much time it takes to run your sequential program. You will now note the final results to verify the correctness of the solution later. So in this case, you can see that there is some sort of terminal output where you are verifying the correctness of the program. And then finally, you are outputting some time. one thing you should do is that you should always run a problem that is sort of representative of the real job that you're doing. Like, there's no point doing an idealized problem which has maximum efficiency if it is different from the real problem that you're trying to solve, because they'll have differential workloads and the actual hotspots and the performance might vary dramatically. So it's better to run codes which are representative of real jobs. Then the second step is to profile a code. So you need to obtain detailed information about how the code runs. This information includes how much the total runtime of the code is, the runtime of the individual subroutines or the functions within the code, and you put in some hardware counters to look at how code is being executed. You then identify the portions of the code that took the longest to run, because we want to focus on these hotspots for parallelizing. Remember, going back to the Amdahl's law, your performance gain or your speed up is limited to what sections of the code that you can actually parallelize, right? So, and you want this code to be as big as possible. If an essentially serial portion of the code is significant, then there is really no point trying to put any efforts in parallelizing maybe 5% or 10% of the code. We did analysis through Amdahl's law, and we figured that if we have a code which is only 50% parallelizable, the maximum theoretical speed up we can get is only about 2. And this increases to about 10 if it is about 90%. So we really need to focus on the large sections of code which A, can be parallelized and are the most time consuming bits. So here's a sample analysis of a code which ran the conjugate gradient algorithm. The total runtime was about 22.38 seconds, and here you can see that the matvec function is taking about 83% of the time, and some other function called dot is taking about 6% of the time. The rest of the time is taken by other minor functions. So this kind of indicates to us that the matvec function is the significant chunk of this program. That is about 83%. So this is our hotspot, and our aim would be to eliminate this hotspot, or rather parallelize this hotspot. The first thing that we would like to do is, first of all, make this function as optimal in sequential code itself. And then finally, once we extract that maximum efficiency from the sequential code, then we dive into making it parallel. So how do we figure out for a general code that, what are the hotspots, what are the functions which consume most of the time? And for this, we have certain tools, and we profile this using the Nsight system and another set of code called NVTX. So we can profile the sequential code using the command line interface, or CLI. So the NVIDIA Nsight systems command line interface provides very simple interface to collect data. It can be copied to any system and analyzed later. The profiles can be both for serial and for parallel code. For more information, enter nsys -- help on the terminal. To profile a serial application with NVIDIA Nsight systems, we use the NVIDIA Tools extension, or NVTX API functions, in addition to collecting backtraces while sampling. So we need to figure out what this NVIDIA Tools extension API, or NVTX library, is. It is essentially a C-based application program interface for annotating events in your code. It can be easily integrated into the application. It can be used within the NVIDIA Nsight systems, which are GUIs, for giving a better graphical representation of what actually goes on. Why is this important? Because it's important because it allows manual instrumentation of the application. Now, a very rudimentary way of doing application instrumentation is to put time statements and printfs in and out of different functions. But that's usually not very efficient. This way of doing things gives you a better control. It also allows you for obtaining additional information from profiling. For example, tracing of CPU events and time ranges. How do you go about doing it? You import the header library, which is nvtools ext.h. You wrap the region or the specific function with two functions, nvtx range push and nvtx range pop. So what does this API actually tell you? So look at this bit of code. So if you do run this nvtx with a -t flag, it selects the APIs to be traced, nvtx in this example. The flag minus minus status, if true, generates a summary of statistics after collection. Minus B selects the backtrace method to use while sampling. The option dwarf uses the dwarf's call frame information, and the minus minus force override flag overrides existing results. So once you run this with this proper formulation, on the left side you have the simple code which has the NVTX functions. So you can see the NVTX range push inits before the initialization function, and then the pop after the initialization function. So you can then go and analyze each of these functions separately. For example, calc next, then you have another function called swap, and you can even do the whole thing for the whole while loop. Each of these regions marked by different colors of start and push and pops of NVTX ranges will now give me information. So what it tells me is that the calc next function takes about 26.6% of the time, the swap region takes about 23.4% of the total execution time, and you can see all this on the GUI timeline. So once you open up the generated report files, which come with the extension QD REP from the command line in the NVIDIA Systems Profiler, you can then see what is called the timeline view. You can navigate through the view selector. An analysis summary will then show you the summary of profiling session. To review the project configuration used to generate this report, you can see the next slide. The timeline view contains the timeline at the top and a bottom pane that contains the events view and the function table. So this is typically the analysis summary on the left side, and then you can see the timeline view, which gives you the charts and hierarchy in the top pane. The timeline view in terms of the event view and the function table are given in the bottom pane, where you can actually go and see function by function how many times each function is called, what is the amount of time that each function takes, and get all the information about this timing. So once you view the captured NVTX events and time ranges via the NVIDIA Inside Systems GUI, you can see pretty much all the information in one particular snapshot. You can clearly identify where the hotspots for the code are, and then you can now decide that what is a function that you would like to first put your efforts into parallelizing. At this point, you can also decide whether that function is parallelizable in the first place at all. Because of many data dependencies, it's quite possible that this function may not be parallelizable. At that point, you have no other option but to abandon the effort to parallelize that function and then focus your efforts elsewhere. So you can also have a closer look at the events captured by the NVTX API from the GUI. You can look at, for example, the while and see how the while function goes through in the bottom pane. You can expand it. You can look at the top pane and look at the charts over there. In the bottom pane, from the function table, you can use a bottom-up view trying to find a specific bottleneck function that can be optimized. In this example, we can see that the calc next function and the cmcopy8, this is actually a compiler optimization that is being applied for the swap function, are places that the application is spending most of its time. After you profile your code, what do you do? Once it is done and once this is optimized, you figure out that this Laplace code now takes, say, 19 seconds on the swap function and the 21.49 seconds in the calc next function. The total runtime is 39.43 seconds. So when you look at profiling the serial code, for example, look at this bit of code where you have some sort of data dependency where output I is equal to input I into 2 plus input I into 2 plus 1. So this is some sort of a pairing function. The input takes an array which is 6 long and produces an array which is 3 long, or half the size. So can we identify the parallelism over here? So we observe that the loops are contained within the identified hotspots. Can we figure out whether these loops are parallelizable? Can the loop iterations execute independently of each other? Are the loops multidimensional? And does that make them very large? Loops that are good to parallelize tend to have lots of iterations to map onto the parallel hardware. Now let us look at how do we profile OpenACC code. So looking at the compiler feedback, you should look at how the PGI compiler feedback for both sequential and parallel implementation of the application is. It provides information about how your program was optimized or why a particular optimization was not made. Adding the minfo flag using minfo equal to accel or minfo equal to all when compiling will enable this compiler feedback messages giving details about the parallel codes which are being generated by the compiler. So for example, in this case, you have different directives for the different functions. Calcnext, where you have an ACC directive, and similarly for the swap function, where you have ACC parallel loop directives. So here you can, once you compile it with the minfo equal to all flag, it will start giving you the CUDA API statistics. Remember what is happening with this Pragma directives is that it's actually creating CUDA kernels underneath in the device hardware, essentially writing code and functions for the device and then calling these kernels. So it then tells you the CUDA API statistics, it tells you the CUDA kernel statistics, it will then give you also the CUDA memory operation statistics and then the NVTX range statistics. So it will then give you further information of how much time each of these functions are taking. You can then open up these captured NVTX events and have a close look at both the serial and parallel implementation. You can notice that the time spent in the while loop has significantly decreased and you are able to achieve a speed up of almost 47 times. So you can do an entire timeline analysis using the Insight systems. Contents of this tree-like hierarchy on the left depend on the project settings used to collect this report. If a certain feature has not been enabled, corresponding rows will not be shown on the timeline. In this example, we choose to trace NVTX and OpenACC while sampling. Kernel launches are represented by blue and memory transfers are displayed in green. Thank you.